Okay, here's an example of compacted soil. It's for a landfill, and in this particular case, in case you're not familiar with it, in the old days we had what? We had garbage dumps where you basically took the garbage trucks to a particular location, you dumped them out, a bulldozer would push the stuff around and mix it with some dirt, and that would pretty much be the end of it. And you can't do that anymore because what has happened is that the garbage, well, especially when it rained, rain would go through the garbage, pick up the different contaminants in the garbage, and carry it down to the water table. And that's no good. So instead, what we do now is we build a sealed, well, dry grave for the garbage. And how do we do that? Well, we put in a clay liner at the bottom, then we put in the garbage, and then we put a clay liner over the top. And it's more sophisticated than what I'm showing here, but there's plastic, there's venting, there's all sorts of things that are done with this. It's actually sophisticated. But the idea here is to seal up this garbage so that it's sealed on the top, it's sealed on the bottom, and the clay, we use clay typically as much as we can because clay can be made with a very low permeability so that water, as it rains here, the water will run off rather than seep through into the garbage. And so when we put down our soil, we need to compact it, and what we're usually shooting for is a soil with a low permeability, for instance, so that it's not only, this is an example of where we don't necessarily need just strength and stiffness. Now, of course, we want the soil to be strong as well, and stiff, and also impermeable. So it's a mix of different things. Okay, now I want to say just a little bit more about in situ testing very briefly. We just talked about one in situ test with a nuclear gauge, for instance, where you put the probe into the ground and measure the dry density and water content of the soil as you're compacting it. There are other in situ tests. I'm just going to briefly mention a couple that are very important. The SPT, which is the standard penetration test. How does that work? We take a sampler, and this sort of looks a little bit like a sampler, and we pound it into the ground, drive it, and what we do is we count the number of blows per foot. It's mainly for a sandy soil. Very simple test in a sense. It can be done at various depths because what you do is you drill a hole in the ground. For instance, you drill a hole in the ground, and then you lower the sampler into the ground, and then drive the sampler down below the bottom of the hole. And so it can be done at numerous depths, not necessarily just at the surface. And we get the blow count, blows per foot. In other words, we drive it, and for instance, if we drive it a foot into the ground, we count how many blows it takes to drive it that foot. And that becomes our measurement, is the blows per foot. And it usually uses the symbol N that represents the number of the blow count. N is the blow count. Now, in this particular case, it's a sampler, so we actually do get a sample of the soil will go up into the sample tube as we are driving it, and we can pull that sampler out of the ground and we can see what the soil is. Now, it's what we call a disturbed soil, disturbed sample. Rather, it's a disturbed sample because the process of the soil moving into the sampler creates, sort of disrupts the structure of the soil. So we call it a disturbed sample. And that's fine. It tells us, it helps us in the sense that we can actually see what the soil is. Next is the CPT, or the cone penetration test. It's more sophisticated. We take a probe and push it into the ground, hydraulically push this into the ground. It takes you have a special truck that pushes. And this probe has strain gauges on it that measure the force needed to push it into the ground, basically. And this test can be used for a lot of different applications. And you get indirectly, you get information about the soil, primarily strength and stiffness, and if you're clever, you can get soil type out of it. Notice we don't get a sample. Here we get a sample because it's hollow. There's no sample with the CPT, so there's a little bit of a disadvantage in that. You can't see, you never actually see the sample. Now, and you never get that sample to take back to the lab. But with this cone penetration test, what happens is that you can push it into the ground and it goes in on a continuous basis, and so you get you don't have gaps in your data. In other words, if you push it into the ground and say the soil changes from a sand to a clay, for instance, you can see pretty much where the boundary is between the sand and the clay. So, two different types of in situ tests here, SPT, CPT, and that's all I'm going to say about them for the time being. Now, I'll say one other thing. For lab testing, well, not all the time, but it's a good idea to have an undisturbed, what we call an undisturbed sample, as much as we can. Now, it's difficult to take an undisturbed sample in sands and gravels, for instance. Much easier to take an undisturbed sample in clays and silts. Why? Because generally the clays and silts are softer than the sands and gravels, and so we can use a thin-walled sampler. In other words, when we talk about the walls of the sampler, here's the walls of my sampler. If the walls of the sampler are thick, then we're going to get disturbance of the sample. On the other hand, if the walls are very thin, then you're sort of cutting into the soil, and you can get it's possible to get a sample does not have much disturbance at all. And what happens is that if you have, for instance, a soft clay or something like that, and you push in a thin-walled sample, then you can get a very good sample out of it. On the other hand, if you attempt to use a thin-walled sampler on, for instance, a gravel, sometimes people make a mistake and they don't know that there's gravel there, and they try to take a sample of the gravel with a thin-walled sample tube, and what happens is that the sample tube is completely destroyed because a thin-walled sampler will not penetrate into a gravel, for instance. So hard to get an undisturbed sample of sand and gravel. However, you can get one in a silt or a clay. So ideally, what we would like to do is get an undisturbed sample and then take it back to the lab and test it. Now, there are ways to get an undisturbed sample in sand, for instance. Very complicated, like you might freeze the ground in advance and then core a sample of the material. That's not commonly done. It could be done under some situations, but it's unusual. And so if you can't get an undisturbed sample, that's one of the reasons we go to the in situ testing, because then we don't need a sample at all. So we like to get undisturbed samples as much as we can. If we can't do that, then in situ testing can be a big help to us. Okay, I'd like to start with a new topic, which is soil stress. And what we need to know is there are two kinds of stress. There is total stress, and we'll use the symbol sigma for total stress. And then there is effective stress, and we're going to use the symbol sigma prime. The effective stress is basically the contact stress between the soil particles. And it includes the effect of the pore water pressure, which I'm going to talk about. So a lot of times what we want to know is what is the stress between one particle and another, essentially. Now, it's not exactly that, but that's the way I want you to think about it, because that's going to get us through a lot of conceptual issues. Now, the relationship between the total stress and the effective stress is that sigma prime is equal to sigma minus u, where u is the pore water pressure. That's the water pressure in the voids. And you need to memorize this expression. This is a very important expression. Obviously, it's quite simple. Sigma prime equals sigma minus u. Memorize that. That's going to, we're going to use that a lot in this class. Now, the way that it works is, for instance, let's consider soil particles and water. And let's say we have a saturated soil here. So this is a saturated soil. All the voids are filled with water. And essentially, a way to look at this is that if the water is under pressure, what happens? The water pushes the particles away from each other. So if I look at that, I'm showing those arrows where the water pressure sort of pushes the soil particles away, and that gives us that the effective stress is less than the total stress when the pore water pressure is positive, if we have a positive pore water pressure. On the other hand, if the pore water pressure U is negative, then sigma prime is greater than sigma. So the easiest way to go through this is to do a little example. So I'm going to determine, we're going to talk a lot about the point of interest. So POI, point of interest. I'm using my point of interest in this particular problem is point A. Point A is my point of interest, my POI. Now, let's review the two rules of water pressure that you learned in statics. Rule number one is that the water pressure acts normal to the surface of interest. And so that's the direction. And the magnitude is the depth times the density of water. So depth times gamma W. So what do we have? So the magnitude is this, depth times gamma W. The direction is perpendicular to the surface of interest. So we have both magnitude and direction for the water pressure. Now, I'm going to consider this soil profile of a sand, and I'm at my point A is 10 feet below the ground surface, and I have my water table in this particular problem is at the ground surface. And I'm going to say that the saturated unit weight of the sand is 110 pounds per cubic foot. And what we want to do is we want to find sigma, U, sigma prime, those three things at my point of interest A. Now, in situ, the pore pressure can be obtained with a piezometer. What is a piezometer? Piezometer is physically just a little tube that can be inserted into the soil, hollow tube, and we have a little filter at the end, or maybe could be as simple as a bag of sand. And if we put a piezometer at point A, so in other words, I put the tip of the piezometer at point A, what will happen with time, if you give it a little bit of time, you insert that, you can actually physically do this in the field. You put this piezometer in place, and what will happen is that water will fill the piezometer. Like I say, you got to give it a little bit of time. You start with the hollow tube, and it keeps filling it until what? Until it comes to equilibrium. In this case, it comes to equilibrium when the water level in the piezometer is equal to the water level in the ground. In this case, the ground surface. So, in this particular class, we are going to, put down, or you're going to put down imaginary piezometers so that you can figure out what the pore pressure is at point A. And how do I get the pore pressure at point A? Well, this tube is just filled with water, and I use my rules. Well, the main rule is this one. The magnitude of the pore water pressure is depth times gamma W, the depth of the water in the piezometer. So here's the top of the piezometer. There's my point of interest, or not the, sorry. Here is the water level in the piezometer. Here is my point of interest. There is my depth. That distance gives me the depth for this expression, and then I just multiply it times gamma W, and that gives me the pore water pressure at point A. So in this particular case, it's 10 feet, so my U is 10 gamma W, which is 10 times 62.4, which is 624 pounds per square foot. So I've got my U, now I need to get my sigma. Sigma is produced by the weight of everything above the point of interest. So I just look at the point A as my point of interest again, and what do I see? Above point A is what? Well, I've got 10 feet of saturated sand there. So that gives me my sigma. So what is that? That's the unit weight of my sand is 110 pounds per cubic foot, the saturated unit weight, and the soil is saturated. So my sigma is simply 10 times 110, which is 1,100 pounds per square foot. So to get my sigma prime, it's simply sigma minus U. 1,100 minus 624 gives me 476 PSF. So we found everything that we wanted. Sigma, U, and sigma prime. Let's try another one. Again, I have sand. I have a gamma saturated and a gamma D. Those are all given. Again, I'm at 10 feet. My point of interest is at 10 feet. But in this particular case, my water table in the ground is at 3 feet depth, not at the ground surface. So how does that affect our problem? We are going to, so to solve this problem, we're going to create this table repeatedly. So we're going to do this a lot in our class. Is we have depth, sigma, u, sigma prime. So the easiest thing to do is to simply make this table. My depth is 10 to my point of interest. Now the sigma, what is it? I look at the weight of everything above my point of interest. And what do I see there? Well, above the water table, I want you to assume in this particular class, we're just going to keep it simple and say that this soil is dry. Below the water table, it's saturated. So whenever we have sand or gravel, we are going to, I want you to assume that the soil is dry above the water table. And so I've given you the gamma D and I've given you the gamma saturated. And I mean, in real life, usually there's some moisture, but I don't want to get into that complication. So I'm just going to say it's dry above, saturated below, and just makes life easier. So what do I have? I've got 3 feet of dry soil. I have 7 feet of saturated soil. So I'm going to have 3 times 100 plus 7 times 110. That gives me my sigma, 1070. Now the pore pressure, there's my point of interest. There's my water level in my piezometer. It's going to be at the water table, and so I have 7 feet. I have 7 feet of water in my piezometer, and that means 7 times 62.4 for my pore pressure. So I have 1070 for the sigma, 436.8 for the U. I subtract one from the other. My sigma prime is 633.2. It's that straightforward. These are easy once you learn how to do it and watch out for certain mistakes. And I'll try to guide you through a way you can make mistakes. So the way I'm going to give you a problem here, let's look at this one. So for this example, I'm going to look at both point A and point B and point C, all 3 of those. And here's my soil profile. I've got gravel, I've got sand, I've got clay. There's my water table. All the depths are given for all the important points. And I'm giving you, now we're doing this in metric, so this is kilonewtons per cubic meter. The depths are in meters. And I have a dry density and a saturated density for each of these. So in other words, the gravel has those 2, the sand has these 2, and the clay has these 2. And I give them to you. I've crossed off some of those. That's the process of the solution. But it's going to make the reason, okay. So the way I recommend you do these problems is the following. You make the same table we just did. We had this table up here. We're going to do the same thing down here. So I've got my point of interest, the depth, sigma, u, sigma prime. When you're making this table, generally you need to have, the sigma has to be big. Why? Because we have to do long calculations. So if you're making your own table, use a lot of extra space for the sigma. So let's start, before we get going, what we want to recognize is where is the soil dry, where is the soil saturated. And what I see here is the gravel is above the water table, so the gravel is dry. So when I'm doing my calculation, I don't need the saturated density. I just need the dry density. So if that's what I recommend as you do these problems that I give you, cross off the one you don't need, circle the one you do need. That's going to reduce errors. Now with the sand, what do I see? The sand is dry up there, it's saturated down there, so I need both of them. So I'm going to circle both of them. The clay is completely below the water table. The water table's up there. And so I don't need the dry density, I just need the saturated. So I cross off the dry density and I circle the saturated. Like I say, that just reduces errors. Okay, so let's look at point A. To get the sigma for point A, I look at everything above it. Well, I've got 2 meters of dry gravel. So it's 2 times 15. The 15 comes from the dry density. I look at point B. Well, what do I have for point B? What's above point B for my... Well, I have 3 meters of dry gravel, 2 meters of dry sand, and 1 meter of saturated sand. So I have 3 gravel, 2 dry sand, 1 saturated sand. So it's 3 gravel, 2 dry sand, 1 saturated sand. So it's 3 times 15, 2 times 14, 1 times 17. I just add all those together. I get 90. Now I look at point C. Well, point C has what? It's got 3 meters of gravel, 2 meters of dry sand, 3 meters of saturated sand, and 3 meters of saturated clay. So I've got 3 dry gravel, 2 dry sand, 3 saturated sand, and 3 saturated clay. And I use the gamma values in the table. Just add them all up, very straightforward. Everybody gets this, it's simple. So I get that for my sigma. What I want you to do is, this is where people make mistakes, is that they use the wrong, if they're not paying attention, they use the wrong density. So don't make that mistake. It helps a little bit to cross off what you're not going to use before you get going with the problem. For my pore pressure, well, what do I see? A, it's dry. It's dry there. There's no pore pressure. So the pore pressure is 0. Point B is 1 meter below the water table. So it's 1 times 9.8. Point C is, now it's that distance, which is 6 meters below the water table, so it's 6 times 9.8. And then my sigma prime is what? My sigma prime is sigma minus u, so I just go 30 minus 0 equals 30. 90 minus 9.8, 80.2. And 187 minus 6 times 9.8 is 120.2. So making this problem's finished, making this table is critical to solving these problems. And it's quite simple. Just have a column, you got the depth, sigma, u, sigma prime. Okay, so I want you to do this problem. So I have, I've got A, B, C. These are all, this is, now notice we're in feet now, so you have to use 62.4 pounds per cubic foot for your pore pressure. Don't use 9.8. And here's my sand, gravel, sand. Here are my densities. I want you to pause the video and solve this problem. And here I've made the table for you in a sense. Oops. You've got, make that little table. Okay, so pause the video and solve this. All right, I'm assuming that you've done that. You've completed this assignment, and now how do I do it? Well, let's look at this. I have my sand. I have some of it is below the water table, some of it's above the water table. So when I look at it, I'm going to circle both of these because I'm going to use both saturated and dry sand. The gravel is below the water table, so I'm not going to use the dry. I'm only going to use the saturated. The sand, same thing. It's below the water table. I'm not going to use the dry. I'm going to use the saturated. So I create my table, and I've crossed off things. I've reduced my likelihood for errors. I'm going to look at, so now I want to do the sigma for point A. Well, point A is what? It's 3 below dry sand. So I have 3 times dry sand, 300. Now I'm at point B. Well, what do I have for point B? I have 5 dry sand, 3 saturated sand, 10 saturated gravel. So I'm going to have 5 dry sand, 3 saturated sand, 10 saturated gravel, and there's my answer. I just add all of those. For point C, I have what? I've got 5 of dry sand, 3 of saturated sand, then 14 saturated gravel, and 4 saturated lower sand. So I have 5 dry sand, 3 saturated sand, 14 saturated gravel, and 4 saturated lower sand. The pore pressure, I haven't shown any piezometers. Well, hey, there's no pore pressure because it's dry, 0. It's easy. Point B, well, I should come along and draw a little piezometer here. And actually, might work better if I show what. If I put in a piezometer, the piezometer is just going to go to right there. Or the piezometer, the water level is going to go to there. Well, what's that distance? It's so this distance right there is 13. So 13 times 62.4 for my pore pressure. Doing the same for C, I draw my piezometer there, and then that distance is 21. So I have 21 times 62.4. And then my sigma prime is what? Sigma minus u. So I simply subtract that column minus that column gives me that column. You can all do that. Check those numbers. Okay, I'm going to stop there.